The limit is of a function is the first concept we will study today. So let's consider first the polynomial function f x2 minus x plus 2, and we are interested in looking how f is behaving close to x when x is close to 2. So the idea is to consider values of f close to an x that is close to 2. Let's start by 1. Okay, here is the value. Okay, so here I'm using Maple, so I'm just computing and seeing how the quantities are changing. Okay. So we see that the values, the f of the x's we are considering are close to 4. So we are expecting that the limit behavior will be 4. Let's see how the graph of the function is. Here is x equal to my function. Yes, the f as x is approaching to 2 from both sides, from the left or right to 2. The fx are approaching the value 4. Okay, so yes, it's good. And the particularity for this function is polynomial. It's defined everywhere, so we can always compute manually these values. Okay, but with this function, there is a problem at x equal 1 and minus 1. So it is interesting to explore how the function is behaving as x is approaching to 1 or minus 1. Let's look at the limit when x is approaching 1. So I need to identify and organize my function, activate it. Here is g, then g at 0, 5. 0, 5 is far from 1. There is a half unit difference, which is important. But these values are close to 1. And we see that we are close, it seems we are close to half when we are close to, okay? g1, 1, we are close to 1. It seems this will be our limit. So let's say we make the conjecture that the limit will be half, which is true. For a moment, we don't know in which sense, how we can explain this. So the graph, here is the graph. So this is the limit where x is different minus 1. It seems that at 1, it's not that problem, even that the function is not defined, but it seems the values taken when x is close to 1, yes, it's close to half. So this is the unit, 1. No, this is 1 unit and this is half. So at 1, yes, it's close to 1. Okay, let's continue with the another function. So you see, we saw function now. The first function was defined everywhere, no problem. The second, it's not defined at the value x equal 1, but it has a limit behavior. Okay, let's look at this one. This one also is not defined at 0. Let's see what is happening then close to 0. When x is close to 0. 1, we said it's very far, so it's not that. Okay, so close to 0, it seems we are reaching some fixed value. Okay, so then the limit will be 1 over 6. Okay, let's graph the function and see again. Yes, at 0, it seems that the function is approaching a limit 1 over 6, even that it's not defined at 0. So these concept of limit, if we can define it well, will allow us to describe really what is happening close to the particular point of the function, where the point is causing a problem. Okay, so now, yes, here I think just I will group it. This is h. Is it h or function? Yes, what I tried here. So first we plotted the function on the interval minus 5, 5. Since we are interested on what is happening close to 0, so I reduced the plot to smaller interval, minus 0, 1 to 0, 1. And here is what we obtain, something almost linear constant function. I reduced more again the interval, and look what is happening. We are seeing some oscillations. So now we are worried, is what is this limit? Is it sure that it is 1/6 here also? There is oscillation close to 0. Okay, so here I regrouped all the graphing depending on the size of the interval. So we need to control, to give description that controls what is happening. Okay, so in part we have to give it, to find some way. Another function, sine x over x, also is not defined at 0, and here is, let's look at what is happening close to 0. It seems it is approaching the value 1. Okay, here is, and yes, limit, if you compute it, it's 1. Here is the graphing again, like, okay, but here also the function is not defined at 0. So let's explore what is happening. It seems it is approaching 0. Okay, so the graphing, but when you compute it, it says that it is oscillating between -1 and 1. Okay, the function doesn't have a limit, it seems. Okay, 1 over x2, look what is happening when x is close to 0. So we are, the 1 over x2 will take larger values, larger. And how we describe when it is getting bigger and bigger, we say that the limit doesn't exist or converge to infinity. Okay, here is the plotting when you graph your function. Here is how it, so when your x is close to 0, both sides, the fx, okay, the fx are getting bigger and bigger. There is also a problem. We need also to give this concept of limit with piecewise functions. Okay, sometimes we have different behavior from one side to the other of the function. So we need to give, look here, L from the 0 from the right. For 0 bigger than 0, values bigger than 0, we have 1. When if you are at the left of 0, you have the value 0. Okay, so here also, here is the graph. The graph is like, it looks like that. So you see, we need to give a meaning. If it is the information saying that I have behavior from the right is important, it gives me an idea. The information on the behavior also from the left. Globally, it doesn't approach specific value, but it is still important to know what is happening from the right hand side. So finally, here is the precise definition of the limit. So we will say that a function approaches value L if whenever we are close to L, very close, we should be able to find an interval, small interval around A, so that all the x's inside this interval take the fx remain in an interval around L of size 2 epsilon. So this is what it says, this statement with symbols. Distance of x to A less than delta, all the x's that are inside the interval, the fx are remaining in the interval L minus epsilon, L plus epsilon. This is the equivalence of this statement. Okay, one-sided limit, we can explain it also like that. We will say that fx will, the limit of fx is L if we stay one side to the right, for example, of A, all the x's to the right of A in small interval of size delta, the fx, the images, will fall in the interval, this interval, not necessarily one side. Okay, similarly from the left, the limit from the left, if for any epsilon as small as it is, if we can, each time we choose an epsilon, we can find a delta, a small interval, so that from the left of A, all the x's take the fx, take values inside the interval L minus epsilon, L plus epsilon. Like that, we control the jumps of f. Okay, we allow this flexibility to jump, but remaining with size difference less than epsilon. And we need also to control what is happening close to A. So this is how we give the first results. We show that the limit, we will say the limit also that fx is L as x approaches A, if and only if the limit to the right equal to the limit to the left exist and they are equal. Okay, so the manipulating this definition with epsilon and delta is not easy. The first two examples, the first for constant function fx equal k, the limit is always k for any x approaching any a. Okay, indeed, because we check the definition for any epsilon positive, we can choose, for example, delta equal 1, and any interval of size 1 will satisfy, since the difference will be always 0, this inequality is always satisfied. So we can say, confirm that the limit is of constant function is itself. The limit of the monom x is a, as x approaches a. Indeed, if you choose an epsilon positive, choose then delta equal epsilon, and then the difference of x minus L is reduced to absolute value to x minus a. So to have this distance less than epsilon, it's enough to choose our delta equal epsilon. Like that, we have these two basic limits, and we will develop next time operations on limit that allow us to deduce more than those limits. Okay, otherwise, yes, manipulating the definition epsilon delta is not easy. We use it to establish basic limits, then we use other tools. We will establish also other tools next sessions. Okay, thank you.